So the next question is, now that we have this summation notation, how do we do actual calculations using this? So there are some rules of summation. One is that if you have a sum, I equals 1 to n, c times I, where c is some constant, then it's the same as c times I, the sum from I equals 1 to n ai, right? So basically, if you have a factor, you can pull it out in front of the sum. Likewise, if you have a sum that consists of a sum itself having two terms, ai and bi, then summing the ai plus bi from 1 to n, I equals 1 to n, is the same as splitting the sum into the ai part and the bi part. Lastly, we have this simple result that tells us that if we take the sum of 1, how many times? Well, from I equals 1 to n, how many times is that? That will be n times, right? If we add 1 to itself n times, we just get n. That's obvious. So here's some proofs of the results. So first of all, we begin by proving this identity. So we take the sum from I equals 1 to n of cai, write it out like this. Then we note that we have a common factor here, which can be pulled outside of a parenthesis. What we have inside the parenthesis here is in fact just what we have here, right? So that's the proof of this identity. The second identity here, we can prove that by saying I equals 1 to n of this sum here. It can be written out like this. That's just the definition, right? Now, instead of having these parentheses, I mean, we can remove all these parentheses because it doesn't matter in which order we add numbers. So we can rearrange this sum, having all the a terms first. So we take the a from here, so on, and from here, and put into one big parenthesis. And when we take all the b terms afterwards and put into this parenthesis, and then what we have here is the sum of all the AIs, and here we have the sum of all the BIs. So we get this result here, which is exactly what we have up here, right? And the last thing was just noting that this basically means that we take n copies of 1 and add them together, which is the same as n. So now at least we have a way of writing sums, and we have some elementary rules of summation. There are also some specific summation formulas that can be handy. The first one tells us that if we take the sum from 1 to n of the numbers, consecutive numbers from 1 to n, so this is 1 plus 2 plus 3 plus and so on up to n, then this is in fact equal to n times n plus 1 divided by 2. We will not prove this, but you can see examples below. First, I will just mention the two other summation formulas here. So if we take the sum of the square numbers from 1 to n, which can be written like this, then this turns out to be equal to n times n plus 1 times 2n plus 1 divided by 6. And the sum of the first n cubes, so 1 plus 8 plus, what is the next? It must be 27, so on. Can be written like this: n to the power 2 times n plus 1 to the power 2, everything divided by 4. So here you can see 1 plus 2 plus and so on up to 4 is 10, right? 1 plus 2 plus 3 plus 4 is 10. Agree? And it turns out that according to this formula, it should be also 4 times 4 plus 1. 4 plus 1 is 5. 4 times 5 is 20. 20 divided by 2 is 10. So at least it applies in this case, right? Now we go to the squared numbers. So 1 plus 4 plus 9 plus 16. What's that? That's 30. 1 plus 4 is 5, right? 9 plus 16 is 25, so 5 plus 25 is 30. And it turns out this is also equal to 4 times 4 plus 1 times 2 times 4 plus 1, like we have up here, divided by 6. So what is this? This is 4 times 5, that's again 20, times, what is this? This is 9. 20 times 9, what is that? 180, right? 180 divided by 6 is 30, so again it fits. Here we have 1 plus 8 plus 27 plus 64, I guess. This turns out to be 100. It can also be calculated like this. So 16 times 25, right? What is that? It's some huge number. Maybe just say 16 divided by 4. That's easier. Then it's 4 times 25. That's 100. So again, the identity holds. And if you like, you can check that it also holds for these other choices of n. Agree, right?